So, dear colleagues, dear lecturer, Professor Raul Jimenez, it is my privilege to announce this lecture now. It is the second lecture in the new tour. We started with the SEENET-MTP online seminar in 2025. And in the description of the announcement, it is announced and underlined that the main reason for these online seminars is to help students in preparation for the school that will be held from 1st to 6th of July in Bucharest. At the moment, we have 49 registered and accepted participants, mostly from the eastern part and southern part of Europe, but all over the world. As Professor Raul Jimenez is one of the lecturers at the school, we asked him, as in the previous case, Professor Dragan Hutter, to give something like introductory lecture to understand the background and to understand the main points in the course that will be held in Bucharest. Professor Jimenez will also be so kind to give a talk on the workshop, on the SEENET-MTP workshop, which will be after the school. So Professor Raul Jimenez is very well known and in the leading scientist in some subfields of the cosmology. And we have something like a privilege to be not the first, but among the first who will have possibility to follow his course, which will be done in 5 or 6 parts. This today is only one part. So I'm very much thankful, Raul, to you. Also, I appreciate all the students and all colleagues who are now joined, and I will not spend your time more. So, Raul, it should be between 45 and 60 minutes of your talk, and up to you. You can announce to the students and to other colleagues to put a question during your talk or the end of the end of the talk. So the floor is yours, Raul. Please start your lecture.
Thank you. Thank you very much, Goran. And actually, the privilege is mine. Thank you very much to all the students that are joining us and sharing this hour with us. I am going to tell you a bit about some work that I'm doing with first-year PhD students. It is complex and it is advanced, but I thought it was a very good idea, rather than reading you the textbooks, which is something that ChatGPT will do for you much better than I can do, and repeat what it is already in every single textbook, to actually take you to the path of research from the textbooks to something that can be relevant to understand the complexity of the cosmos. And the title will become apparent to you very, very quickly, and you will understand why I call this series of lectures The Complexity of the Cosmos, and also why the main aim is actually to try to simplify and understand the universe in a reductionist manner in simple terms, if possible. What I'm going to show you is an attempt to do that. For whoever doesn't know me or knows what I do, the best thing you can do is to go to my website. There are papers, books, publications, code, especially code, that you can download and play with. There will be this series of lectures that I'm going to do today, because of the format and because we were going to do it in Zoom. I thought it would be good to talk about something more theoretical, but I have divided my lectures in 2 parts that I think are going to be interesting. One is the theoretical part and the theoretical approach. The other one is going to be teaching you machine learning techniques to solve complex problems. And by this, I mean techniques that can be applied just today in very complex problems that involve nonlinear PDEs. And I'm going to teach you some techniques that can be executed over the cloud on the web. And we will do exercises when we meet in Bucharest to actually address this part of the problem. So as Goran said, it will be a few lectures that I will be walking through this, but my main aim is going to be to try to understand the cosmos without complexity, or try to understand the cosmos in a simple manner. Now, you're going to spend with me 5 hours probably, or something like that. There's only one lesson, one single thing that I want you to learn out of these lectures. The rest is to some extent irrelevant, because you know it is something that can be worked out, and it is the following. If I can just manage to, is please never lose your curiosity as a kid. Keep doing it as you grow up and become a scientist. The only difference between a successful scientist and a mediocre one is the thrive of curiosity. So as much as my daughters were curious when they were babies, I want you to transmit this theme into you about becoming curious and keep searching for understanding the universe and the cosmos. Okay, so what am I going to say and what am I going to talk about? It's going to be 2 parts. Most likely, I will only be able to touch upon the first part, because I put a lot of overheads, right? But both projects that I'm going to tell you about are done with PhD students, first year PhD students, and you know, have some pictures of them there. And you know, try to see what we have done. So I'm going to start pedagogically, and I will slowly increment the level of the talk, of the lecture. So the first part I want to tell you about is how can we understand the quantum nature of the universe. If the universe is simple, we believe it is fully described by quantum physics, by quantum mechanics. If that's the case, is there any way that we can actually figure out that the universe was quantum at the beginning? This is what is happening, right? Every observation you do of the sky today with a telescope, everything that you observe from galaxies, from the cosmic microwave background, to gravitational waves, which are actually classical objects, are classical. There is nothing quantum in the universe from what we observe. But we believe the universe was made quantum at the beginning. The question is, how can we figure that out? So this is something that connects 2 worlds, the worlds of cosmology and the world of quantum experiments, of quantum, what I like to call quantum gadgets, if you want to say it, quantum optics, because the idea is to use the techniques from quantum optics and from quantum experiments to actually figure out if there is a signal from the sky that can give us some hint or some clue about what is happening in the universe. So let me just remind you slowly about what is going on. So it is something that I call an entangled universe, and I'm going to tell you why we call it like that, because of the quantumness of the problem, right? So let's try to recall how the classical picture, the classical in the sense of historically and most adopted picture of the universe looks like. So we believe that inflation is the driver behind the structure and the size of the universe, in a sense that there was a certain point early on in a scalar field. This scalar field produced a kind of quasi-de Sitter vacuum energy. And is this vacuum energy that forced the system to inflate, because the pressure is equal to minus the density from the equation, very close to minus the density from the equations of motion. And more importantly, is that the reason why we like this paradigm, this model, is because it also produces the fluctuations that are going to lead to galaxies. So quantum fluctuations in the fields present during inflation, just simply one single scalar field, the rolling down, get stretched by the exponential expansion to cosmological distance. So in this little plot, I'm showing you the size of the physical size on the y-axis and time on the x-axis. So you have this field inside the de Sitter horizon. Of course, de Sitter has a horizon. This is important. This is very important, actually, if you want to make inflation. Inflation will not work in a Minkowski space. This is a simple exercise that you can actually do. You have a little fluctuation because if we believe that nature is quantum, there will be some fluctuation that is going to happen. There will be the vacuum will be fluctuating, the fields will be fluctuating all the time. But the fact that you have a horizon and an expanding universe means that the size of this physical perturbation is going to go proportional to A, while their amplitude decays as A to the minus 1. The horizon remains almost constant, a little bit modified by the slow roll parameter, but almost constant. And therefore, what is going to happen is what you expected. This thing is going to get out of the horizon, this fluctuation. It is this stretching that it is allowing the fluctuations to grow and actually to survive. So it's crucial that they get out of the horizon. So any co-moving fixed wave number k, the physical wavelength of the quantum fluctuation generated inside the Hubble horizon will soon become larger than h to the minus 1, the size of the de Sitter horizon at that point. At some point, and this is done by hand, this is something that if you remember, you can have a scalar field that it is slow rolling, but at some point you're going to have the so-called gracious exit basically by hand. You're going to drive out the system out of this slow roll regime, and therefore the pressure is not going to be any more equal to minus the density, but the pressure is going to be equal to the density or something like that, or the pressure will be zero if you believe there is only dark matter, collisionless dark matter, and therefore inflation will stop and the system will start to come down. That means that at this point, the fluctuations are not able anymore to be stretched out of the horizon, but are going to come back to us. And it is when they come back that we are going to see these density perturbations as the classical seeds for the formation of large-scale structures. Most that left the horizon the latest will be the first ones to re-enter, and vice versa. For the most of cosmological interest, those responsible for the large-scale structure, that is avoiding non-linearities, we are talking basically about something between actually 10 megaparsecs to 3,000 megaparsecs. So basically, we just need to have these fluctuations to re-enter the horizon today. I mean, if you wait another 100 years, you will have fluctuations that left earlier than the ones we are seeing today. So in principle, if you were able to live for 1,000 years, or you can have a robot or AI system doing observation for 1,000 years, you can actually see how this time, how the fluctuations are entering as a function of time. So, you know, this is something maybe people can think about, futuristic experiments that lead you to such a measurement, right? It's something that one can explore in the future. So the motivation for this exploration is the following. We treat these perturbations as classical. When did the quantum to classical transition occur? Can we find some trace of the initial quantumness? That is there any hope that the system will be not, it will have some memory of the quantumness that it had at the very beginning before they became classical, right? So this is basically the question that we are asking and we are wondering, right? Is that given the fact that all the classical data we observe are classical, how can we look for quantumness? Somebody can ask me, look, you are of course made out of quanta, you are in a Schrodinger equation entity, but you have so many molecules in your body that already you have interacted with environments, you have decohere, and you are almost purely classical, right? So is there any hope that I can see any quantum effects in your body? so you can be skeptical about this path because you can say, there should be no hope. But here things are different because you have a horizon, and the horizon is allowing you to do things in a strange way, as you will see. So it is crucial, the fact that you are having a horizon. Somehow it is allowing you, it's like a dictionary that is allowing you to talk back and forth between classical and quantum. So, of course, as I give this lecture, and as I said, just make room for myself here. Okay, very good. There is a question that still is, so in this lecture, basically what I want to do is to motivate question and open problems that you may want to pick and say, oh, this is an interesting open question. This is something that maybe I can start doing my PhD on, right? Or my early master, or whatever kind of things you are doing. So one of the open questions is how this transition happens, right? How do you go from classical to quantum? So let's try to start making some more quantitative statements and actually go into a more higher level trying to address these questions, because otherwise it is not possible, right? So let's think let's think about the following scenarios. So what it is guaranteed early on in this inflationary universe is that we're going to have the gravitons and the quanta of the inflatons, right? So inflatons. How can we get an entanglement system of these gravitons that can actually survive and tell us something about what happened early on? So what one can do is the following, right? Build a Hamiltonian for this entangled system of gravitons. Suggest a mechanism by which the entangled states are created during inflation. And then build a coherent state of this graviton such that it acts as a pump field, like when you do experiments on the laboratory with a laser. Basically, the laser is your pump that is sending you this information about the entangled gravitons. Then one can just go and describe what could be the observable for seeing this. So let me just go about this thing. So I talk about entanglement. Let me just be pedagogical and go back a step and go back to the books and see what I mean by entanglement and why I say that this is the most quantum that you can have, right? You know that usually you talk to somebody in quantum physics, they will tell you, well, look, if you have a system that is entangled or it is a squeeze, there is no way it can be classical because this is the most quantum that you can be. So basically, entanglement is the main aim or the most precious aim to actually understand what is happening. So entanglement between two quantum states is present when the quantum state describing the whole system cannot be written as a product of the state describing each subsystem separately, right? I mean, that's why we say that the system is not separable, right? You cannot make tensor products of the two states to actually make your current state. You actually have to take into account the cross terms. And yes, you can see entanglement simply as a consequence of the superposition principle in quantum mechanics that makes the non-locality explicit. So let's try to write this down, right? You can just go here. I don't know if you see my cursor or not, but you can just write the state as tensor product of these A and B, right? Of course, properly normalized. So entangled states are pure quantum states. So you want to be more mathematical, a bipartite system. Since they can be described by a vector state phi or psi in a Hilbert space, and more importantly, they cannot be described by a product of separable states. So if we choose to describe each system in subsystem individually, if I insist that I want to do that, I say, well, I'm going to do this because I really want to do that. Then you find yourself that you can write it as a vector, like here, but you have to mix, right? And this is what is happening in this case. Very good. So let's just try to be a bit more precise, describe the system a bit more so you understand what quantum entanglement is. Take here a particle Alice and a particle Bob, A and B, and then there's just give them like their corresponding states, and the same for B. Now I make a measurement, right? So I go, I look at, I mean, and important to remind you that in quantum mechanics, a measurement is not that I have to make a measurement. A measurement really means that there is an environment. So if I was a single electron in a flat Minkowski space infinite, then I will stay quantum forever. But the moment there is something that goes away from just being a single electron, then I'm going to make a measurement. And then if the system is entangled, then you get the classical thing that if you make a measurement, you know exactly how the state of the other should be. So this is the classical spin up, spin down. If you measure one system to be down, the other one has to be up. I mean, this is not very surprising because this doesn't happen with any random system. It is not if I measure here the spin of a ferromagnet, I know that the one in Andromeda galaxy is going to be down. No, it means that if I prepare a system that is entangled, and then I separate them from each other, keeping quantumness and not collapsing the system, then I know what is going to happen. So this is a special setup because the system has been prepared in a particular way. And this led to the famous Bell experiment, you know, that there must be a clear difference if this is the case, that you have these non-local effects between a quantum system, a pure quantum system, and a classical system where you have hidden variables trying to mimic the effect of quantum mechanics, right? You could just say that, no, okay, the system is classical, but underneath there is some kind of a theory that I don't know about, that it is actually making this thing go this way. So what we need to do here in the inflationary paradigm is a bit different, right? So I'm going to have two separate spatial locations. I'm going to call them Alice and Bob, right? And I'm going to generate an entangled system. Now, Alice and Bob are going to be gravitons. The reason I'm going to choose gravitons is because A, I know they are there all the time. Gravitons are guaranteed to be in a de Sitter system if gravity is quantized, but I'm going to assume that's the case. And the other important thing is that because gravitons are a spin-2 field, then I'm going to have polarizations of this object that is going to make it very easy to create entanglement, and then later maybe measure it. So just basically, I can just take or look at each observation as represented by non-commuting operators. Let's call them A theta 1, A theta prime, B theta prime, respectively, right? And then I can define an observable. This observable will be something that then I can relate to actual observables in my universe, in my telescope, right? Which I'm going to define like this combination, right? I mean, of course, just the permutations of these thetas, where I have this C defined as the expectation value for some observable for Alice and Bob. So the nice thing of building this observable is that S is such that in a description with a classical local hidden theory, where the measurement of S is uncorrelated with the measurement of B, I violate Bell. So basically, this is the Bell theorem. It says that if I have purely quantum mechanics, then S should be smaller than 2 square root of 2, while if I have a classical system with hidden variables, it has to be smaller than a square root of 2. So basically, in quantum mechanics, S can be smaller than 3, but in classical physics, has to be smaller than 2. So if I measure something above 2, then I already proved that the system is quantum, that it cannot be described by a system of hidden variables. And this is basically what has been going on for a long time, many Nobel Prizes given to actually the actual experimental demonstration that happened, right? For example, Clauser and other people. Now, in our setup, I have two separate special locations, call them Alice and Bob location, and I create an entangled state of the type as I describe in this equation. I have two possible measurements of some physical observable. We will describe later what it is, whose result is going to be dependent on some local variable, that is the angle, for example, the polarization that you are going to measure. And what I want to do is actually to measure an S quantity in such a way that I can discard the classical result. So just to remind you, technically, it is very useful to work with these two states known as Bell states, which are defined as this plus minus the psi and the phi are defined in this way, right? So what would I need to do in the skies to reproduce a Bell experiment? This is a question that you can ask yourself, is to say, okay, in the laboratory on the ground, I know what I have to do with photons with a laser, right? You have to split the beam, you have to prepare the system, and then measure it. So let me walk you through this thing, right? Remember, let's go back, that I'm going to work with these Bell states, okay? This phi and psi that I'm going to take in order to actually make the things easier. So I take this state, I have Alice and Bob, I send them around, I make a choice for the measurement for the thetas, right? Theta 1, theta prime, theta 2, theta prime 2. And I try to make a final observation, right? At the time that has to be where I am, right? That it is outside after inflation took place. So because I cannot go into inflation, I need to have an imprinting at that time of inflation that leaves a signal that I can actually measure. So as you remember, a graviton is a spin 2 field. So I have the plus and the cross polarization that you can look at this like oscillating circles, ellipses in these polarizations, and you know what you can do with it. I mean, in the sense the following, right? This is how you build the Bell state precisely with the polarizations. So let's create a coherent classical state for the inflaton field at an early stage. And this will be the pump or the thing that is going to give us this entanglement at the very beginning, right? I can do this with the following Feynman diagram, right? Here are the gravitons to graviton and Wien scalar, right? So if I look to third order in perturbation theory for this kind of Feynman diagram, right, where I have the inflaton and two gravitons, then automatically I can build this kind of entanglement. And I do that by building the following Hamiltonian for the interaction that I found at this third order in perturbation, right? Well, you don't have to follow now the equations, you can do it offline. It's not important, but I want to be complete. So, this is basically how you are doing it. Very good. So this is how I created the pump, the entangled system. I created the entangled system by using this interaction between the gravitons and the inflaton that I will have there. Nice, I have the first step. Now I want to try to do the imprinting of the measure, right? So how do I do this? Well, there were some recent papers by Wald and collaborators that are telling you that basically every time you have a horizon in a system, and you have a system that gets close to the horizon that is entangled, you are going to have a measurement produced on it. So this is nice because in our setup, we do have a horizon, which is the de Sitter horizon, right? So the cosmological horizon is almost a Killing horizon. So we can take a cosmological horizon as our way to perform the measure and induce the collapse of the wave function. So basically, I can follow this formulation in the paper that I quote here, and it is very nice to read. And basically, that is going to be the equivalent of me going with the magnifier doing a measurement. Nice. So I have the second part. I keep building how I get to the thing. So now I have to say, okay, unfortunately, I'm not sitting in during inflation. I wasn't there, so I could actually measure the polarization of the gravitons and move from one side to another and do it. But I want to pose a question to the students that maybe we can discuss in person in Bucharest on the blackboard. That today I'm almost in the sitter, right? We are lambda dark energy dominated. I'm sure that Dragan told you a lot about that last week, about how Desi is unveiling the fact that we are in dark energy and maybe this dark energy is evolving. It's interesting prospect. But of course, I'm inside the horizon today, right? So I'm generating the same kind of fluctuations. I'm generating the same kind of processes that I'm talking about now. So somebody will see them in the future, right? When this inflation epoch finishes, right? And then the next people see what is happening. Now, the curious thing will be, can I see them today? Is there any observational thing that I can do since I have the luxury to be sitting inside the sitter horizon, which is what is happening now, right? I'm basically inside the sitter. So now the way you do this is a bit technical, but it is interesting to connect it to the part that Dragan was telling you about large scale structure, is that basically after at horizon crossing, just before you are going to just leave the imprint, you're going to have this interaction that it is called graviton exchange, which is between a graviton and two inflatons. And actually it's a two inflatons, graviton, two inflatons. So you have this vertex here, right? And now this is interesting because if you look at how this signal is computed, this signal here is actually computed by integrating over polarizations. So the classical thing to do is you ignore the difference in the polarization and you say, okay, I don't care, I average all the polarizations and I get the signal. But this signal, by the way, is going to produce a non-Gaussianity, basically. Small, these are small things, small signatures, but it's going to produce a signal. Now, if you take into account that maybe here you're having a decoherence and entanglement, then it's going to matter which polarization you have, because there will be regions of space where things are mostly plus or things are mostly cross, right? And therefore you are going to have this kind of effect in the sense that now you are like looking at a peculiar thing. So this proposal is telling you there may be a way to actually pull out the quantum signal from the early universe that give us a hint that the universe was purely quantum. And therefore, that I can have an insight of what happened in an environment of pure quantum gravity without having things that I cannot reach on an accelerator today on Earth. And that is going to give me an insight into that. This is one way to do it, but it's the way I wanted to present to you. So basically, this is the summary and conclusion of the first part, how you actually construct a Bell experiment in the sky that can give you that. I'm going to finish in 5 minutes. I'm not going to go over the whole second part because I want to do this part when we are in Bucharest, but this is the next step in the project of making everything quantum. Now, if I make everything quantum, things are very easy because I can then make a distribution that is the most economically possible, right? So this attempt is something to make inflation without an inflaton. In other words, usually what happens is that you put in the inflationary paradigm, and I gave you here a lot of references so for the students to learn or ask ChatGPT to read them for them and tell them what it is that it is important. But the idea was to have a scalar field that is doing the job of a quasi-de Sitter. What we will post here in this paper is the following. Because this scalar field is basically arbitrary, basically you can draw it by hand, basically, and then you keep adjusting the shape of this potential according to the observations. It is therefore a bit dangerous to have such a arbitrary thing in a model where the model is not only a parameter that is free, it's a whole function that is free. So here we said, okay, let's assume that I have the sitter, okay? Something very simple. Imagine that somebody is giving me the sitter. Can I make inflation in the sitter? Well, there are two problems there. Is that to say, okay, how do you make the scalar fluctuations to give you the galaxies? Because you are guaranteed to have a lot of tensor fluctuations. And that's very interesting. But how do you generate the scalar fluctuation to overtake the tensor fluctuations? And also, how do you get out of there, right? Because, of course, you can be in the sitter, but the sitter is a place where you cannot get any energy out of, any work out of it, sorry. Because it's like a table, right? If you are sitting on a table, in a perfect table, imagine a perfect table, if you don't have any energy, you don't move, you stay there all the time, right? It's only when you tilt the table that it's Galileo, back to Galileo, right? I mean, basically inflation is like Galileo inclined plane. It's basically, if you move like this, then the force of gravity is going to send you somewhere, and therefore you can roll fast. Well, so what this work did in the physical review letters now is that actually propose a model to do that and to generate these perturbations. And I'm not going to go into detail into that because I think it's very arid. I'm going to stop here, which is 45 minutes. There was quite a bit of material, and I think I will take some questions from the audience or whoever wants to ask any questions. Thank you.
Thank you, Raul. I think it was very informative. I think it was very useful, not only for the students and from all of us. And now it's time for the questions. I encourage anyone to put a question because I think it's also interesting. It connects several fields of physics. It's a really complex question and in a sense simple model through its complexity.
Exactly. Of course, when I'm in person in Bucharest, I want to discuss this thing on the blackboard. Is much more informative, and then we can just look at these things in more detail on the blackboard. So if people want to delay questions for Bucharest, that's also fine with me, whatever you prefer.
Okay, thanks again. So please, now it's time for questions. I think I saw a few seconds ago a raised hand from Professor Miroljub Dugic. It's true or not?
Hello?
Hello.
It's Victor Ovidius Lupik, I think, isn't it?
Yes.
So
Please, Victor.
No, I don't have a question. Sorry.
Okay. I noticed that you are. No, I told that I think I saw two raised hands before. I think one was from Professor Dugic, another one from Banja Luka. But anyway, I have one question in the
Yes,
meantime.
please.
So I think it's a very general but also very important question, and I think that for the students it would be very good to understand the importance of the model. Namely, you mentioned at several points in your presentation, I beg your pardon, that your model is based practically on only 6 parameters.
That's true.
Am I right? Yes.
That's correct. The Lambda
So,
CDM model, yes.
to compare it, I think, Raul, it would be very useful to compare it with the current standard LCDM model, and how many parameters we have there, and can you compare very shortly about the
So
same and the similarities and differences in that?
So that's very important question. So in the current Lambda CDM model, we have 6 parameters, right? Actually, we have 4 plus a function, plus a free function, and that's what I want to emphasize. So what are the parameters that enter in the model in the Lambda CDM? Well, we have the Freeman equation that requires the energy density, so omega matter, omega radiation, and omega lambda, right? Okay, you make it flat, then you only need one of those, but that's an assumption. And then you need a H naught, right? Because you need to fix the expansion rate of the universe at some point, either today or at the early time. So you need the Hubble constant. Plus, you need the generation of the initial state, and that comes through the inflaton. But the inflaton is a free function. It's a function that we don't have any constraint on. So I would say that the standard Lambda CDM model has 4 parameters that are numbers plus a function that is free. What I'm proposing is to actually eliminate the need of the free function and just have only the 4 parameters. So in this case, it is a reduction, a significant reduction of the number of free parameters, because you basically get rid of a free function.
Okay. Yes, Professor Dugic, please.
Thank you very much. Thank you for very interesting talk. I have one question regarding the decoherence time. Is there any estimate for the scale of the decoherence time in any of those models? I'm just a layman in the field.
Yes, so the coherence is actually quite fast. So I don't remember now the numbers from the paper, but the coherence should happen, basically the only scale that you have at that time is the 1/h, where h is the zeta horizon, right? So the coherence takes place basically at that time. It's the only scale in the problem, right? There is no other time. There is no other clock that you have there.
Yeah. Okay, thank you.
Sure.
Okay, so now it's 5:47. We have a couple of minutes more for one or maybe 2 questions more, if any. Okay, so maybe Raul, we could use now use 1 or 2 minutes. Maybe
Yes.
you can explain to the students in which phase will be the course. So they will have free full talks and one slot
Yeah,
for tutorials.
exactly. So my
Because
plan,
now we have more students than it used to be, I think it's good to just tell them what they can expect from. Just a second, I think your first lecture should be on 3rd of July and the last one on the 6th of July, if I remember well.
That's correct. So my idea is that on the 3rd, I want to do the second part of this lecture and give a full picture of the theoretical cosmology. And then in the next 2 lectures, I'm going to dwell on the aspect of machine learning, artificial intelligence, and how to actually solve anything from Einstein equations to Navier-Stokes or any kind of PDE using machine learning, and what are the advantages of that. And in the last day, when we have the tutorials, I will propose the students online exercises to actually execute these ideas on machine learning. So it will be an interactive session where you will just get your computers, you go to the Colab Google website, the free one, no need to pay anything. There will be a Python notebooks there that you can execute simple things, and you can see how you can solve complex differential equations using these new techniques and these new methods that can help you, well, first to understand all the revolution in artificial intelligence, but also know how you can use that in the context of physics, basically, right? Because I will be dealing with partial differential equations directly.
Okay,
So that's going to be the structure of the course.
very good. Okay, I think there are no much questions. I think for the students, it was at least I triggered their interest because it's the presentation of the cosmology in a bit different way. I mean, through also the quantum mechanics and
Right.
these things. So I think they will start or continue their preparation for your course. We will be in touch. If there will
Of
be a
course.
possibility, maybe we will also add to something of the literature or some literature to propose to them. Otherwise, the course is pretty much compact, and I think it can be easily to be followed there. So I would like to thank Raul again. I
Pleasure.
forget to say that Raul is basic affiliation is in Barcelona in the leading
Right.
institute there for cosmology and related fields, and also with affiliation at London and the Princeton Institute and many other institutions. So Raul, thanks again, in particular for your coming to Bucharest and for the
Sure, of course.
giving contribution both to the school and the workshop which will be followed. Thank you for your attention. Thank you for your questions, and keep in touch and see you soon. I hope all of us in Bucharest.
Thank you very much. See you there. Bye bye.
Bye bye. Ciao.